Let's now talk about the multivariate classification. So we are using the idea of multivariate distribution to do some classification. If we are looking at the conditional probability density for classes, we are looking at these things. So this is a likelihood. So it's a probability density or likelihood of having an X given that we are in class Ci. So what we do here for classification is that we assume that each class is following a different Gaussian distribution, and that Gaussian distribution for class Ci is characterized by two parameters, the mean vector for class Ci and the covariance matrix for class Ci. So given this, we say, okay, if we have three classes, we have three mu's, three sigmas, three big sigmas, and that is describing basically the distribution of points. So we just state that the samples from class Ci is following a normal distribution characterized by this mu I and sigma I. And the equation here is giving us this probability density. There are some reasons for using normal distribution in multivariate classification. The first one is that this equation still somehow simplify a lot of developments. So when we are making analytical developments over this equation, the fact of having an exponential, and we are looking often to manipulate the log likelihood, simplify things quite well, and it's kind of manageable in terms of mathematical developments. It's also a relatively good model for describing many natural phenomena. Often we consider observations, or we are observing things that are similar, so from the same kind of things, but with slight variations. So we can say we have a mean representing values for that concept, and we have slight variation around it, and the spread or how they are distributed around the mean observation is described by the sigma. So the sigma gives us that shape around the mean value. And it's a robust model. You know, it's good for making approximations. It's relatively good, fitting well for many situations. It's kind of robust. It's not sensitive to small artifacts that may make the distribution quite different. And when we are estimating the mu and the sigma, we tend to get into relatively stable values with not that much samples. But it is still based on a strong assumption. This assumption is that data are grouped together. So it means that if we are data with two modes, an example of two modes, maybe for example, with unwritten character recognition, for example, there are many ways to write the letter A. For example, we can say, okay, a letter A can be like this as capital letter, can be like this as a small letter, but can be like this. It's more typographic way of writing A's. So these three ways of writing A's are much different in terms of just the strokes of my pen on that. I have much different strokes. The look in terms of image is much different, but still these are relates to the concept of letter A. So we can see here that we have three different modes, at least the mode for the capital A and the mode for the small a, and this one may be associated to the second one, depending on how we see this. And as such, using a Gaussian distribution here doesn't make sense because we will need to model two different things, and the average for this concept is different from the average from that concept. And if we try to merge all of them together, we'll get an average concept that is neither the capital or the small letter version of A's, and it will not be that good. So we need to consider mixture distribution, mixture models, which are linear combination of several densities. We will see that later on. So if we have an example of multivariate classification here, we have two classes, an example with two classes with different configuration. So we see region one. So we see here, this is basically the distribution for class one. It is kind of well-rounded distribution. The distribution looks like this, so it's kind of regular. We have the other one, which is more spread along this axis here. We can see it in 3D here. So this is quite different from the other one. The mean is different. The covariance matrix is also quite different. But if we look at doing classification with it, what we are looking at is basically the assigning a sample to the class which has the highest posterior probability. And if we simplify equation, what we saw with the Bayes decision theory, we can get into something like this. So we can say, okay, in that region, we are looking at this function. This is basically the distribution of for the class, so the likelihood for the class CI times the prior probability for that class 1. Likewise for the second class, and we just assign samples to the class which has the highest probability or highest values in that. And we can see that curve. This is really the frontier. So everything in there is from class 2. Everything in there is for class 1, which is the same thing here. And we see this is the point where both distributions are crossing. When both distributions are equal, this is where we have a frontier. So if we look at the discriminant function we get from that with multivariate model, we can directly look at the log likelihood. So we can state that the H function for class I for a given X, assuming a multivariate model based on normal distribution, Gaussian distribution, is equivalent to the log of the likelihood for the class CI plus the log of the prior. This is basically our function. We get rid of the evidence, so the PX, sorry. So we don't care about PX here. Wait. The PX here is not used anymore because it is invariant to the class. So it is the same for each age. So we don't use it. It is not useful in terms of decision. So for a normal distribution where we know that the likelihood is following a Gaussian distribution in d dimensions with mu I and sigma I as parameters, we've got that thing. We have HI is equivalent to, so this is basically applying the equation of multivariate normal distribution. And we are able to simplify many things. First, we are simplifying this because it doesn't include X, so it's the same for all samples. So we don't need this. It is, and this is the same also for all samples over all classes. So it's a constant that is not useful. This thing here is kept. It's basically one of the terms before the exponential that is useful when we are kind of dividing by square root of sigma I in 1D. This is equivalent here with the determinant of the covariance matrix. And that part here is what is in the exponential. And the last one here is basically the prior. So we are taking the log of the prior here. Now the question is, how do we do the parameters estimation based on maximum likelihood? So we have a data set here, which is made of X's, and so these are the vector of values for each sample from 1 to n. We also have the RIT vector, the RT values, which are put in the RT vector, which are the labels. Basically, if a sample belongs to class C3, for example, the RT vector will be made of 0, 0, 1, 0, 0, 0, 0. So it's a one-hot vector, only one value equal to 1, all the others equal to 0. And the size of that RT vector is the number of classes. So if we have key classes, we have key values in RT. So the estimation of the prior probability, so we can estimate it, is, so that's why we have the little hat. So P hat CI is equivalent to summing the ART. So we are making a sum of our ART divided by n. So we are counting the number of samples for class CI, which is from that class. So this is the number of cases where the RIT value is equal to 1. So it's a simple way to count the number of samples from that class divided by the overall number of samples in the dataset. Then we are computing the mean vector. So the mean vector for class CI, it is basically summing using the RRT as indicator. So that's really nice. This is where the notation really makes sense where we can directly use the RRT as a way to activate or deactivate the summing of xt. So we are summing over all samples, but the xt is contributing only for the cases where it is associated to class CI. So this is when the RRT is equal to 1, because otherwise it is equal to 0. And we are dividing by the total number of samples from class CI. And as for the covariance matrix, we are doing the similar thing. We are computing the covariance as usual, but we are using RRT here to somehow activate or deactivate the elements that are from the class CI. So we only activated xt that are from class CIs. Otherwise, we are multiplied by 0, so that's canceling it, dividing also by the number of samples we have in class CI. Now, if we look at quadratic discriminant functions, we are looking in the case, in general case. Now we have the function hix, which is basically our discriminant function, which is built from the estimation. So it is basically what we had before, with the exception that we are changing the mu for the m and the sigma for the s. So we are using estimations instead of real values. And as such, we have -1/2 log determinant of covariance matrix SI. And we have all these things here, which is basically the same by using the estimators, and we have the log of the higher probability. If we are decomposing this, we can get into this formulation. So looking at this directly, if you look at this, you can see that it is a quadratic function. Well, if it's not obvious for you, consider this as the vectorial equivalent to the 1D function of ax2 plus bx plus c. You know, something that we see at, we've been explained at high school, an order 2 equation with ABC, which are constants, coefficients, and x squared, which is the squared value, which is basically coming from the fact that we are multiplying x transpose with x. Likewise, we have this x here, which is basically that element there, and w10, which is basically the constancy. So going back to this thing, you know, we have this general formulation of a quadratic function, which map to that thing by using wi as this thing, so capital Wi here, small wi as that thing, and w10, the constant, as this thing. So these are all independent elements independent from the x, while this thing is basically coming from when we expand this thing. So we've got the s inverse of si times mi, and if we are looking more, so that thing is basically also coming from that expansion. But you know, if we are looking at the constant, the nice thing is to see that this is constant according to the x, this is constant according to the x, and this is also constant. And that last part come from expanding this part where we have the 3 elements. So if we are looking at example of quadratic discriminant functions, we can look at these things. So we have 2 classes. So each class is following one Gaussian distribution, one normal distribution in 2D. We can see that with these 2 classes, we have different distribution, different covariance matrix. And then we have a decision frontier that is like that. This is really where the 2 distributions are equivalent. Likewise, we have this thing here where we have something that is well concentrated. So you see this distribution for this class is well concentrated there. So we have a decision frontier that is around that peak, and all over the domain out of that peak, we are associated to the other class. Another example here. So we see that these decision frontiers has this kind of curvy look. These are the quadratic function. So basically the decision frontiers are following a quadratic function that look that thing. And so we have something here that looks like a kind of oval. because here it is well concentrated around the mean. So this is really where we have a higher value, and otherwise in the domain we are associated to the other peak, the other class, which is flatter, but the spread is bigger. So when we are far away, still that value, the value for that class is higher than the value for the class that is well concentrated around the mean. And now if we are looking at other cases, we can see interesting stuff like this thing here. We have two functions. In fact, we have this two frontiers. So we have this frontiers and that frontier. What that means is that this class with the light gray is spread all along that line. So in all that region here, it belongs to that class, but also in that region there, because somehow, given that it is spread in that direction, it tends to have a higher value there than with the other distribution, which is spread more in a not perpendicular, but quite in perpendicular direction compared to this one. So the spread in that direction is much lower with that the second distribution, which is spread the other way around. And the last case is when we have two distributions with the same mean. So the mean is the same. They are both centered there, but one of the distribution has a really narrower peak. So the determinant is different from the other one. So it is much more concentrated around the mean. So that means that we have something with the decision function around it. Inside, it is with the dark gray distribution, and outside, it is the light gray distribution. One thing to consider with such thing is the curse of dimensionality. So working in multiple dimensions is super interesting. In fact, it is required to deal with most problems. But the point is, when we add more dimensions, when we add a dimension, it creates an exponentially increasing the mathematical space. So that's kind of scary. Like the curse of dimensionality is also a scary term somehow. But the point is that, yeah, we need to be cautious because working in high dimensionality is really hard to manage. It doesn't behave as we might expect in 2 or 3Ds, because the space become more and more empty as we increase the dimensionality. For example, if we are dealing with 100 points, which are equidistant from 0.01 in one dimension, so we have really just the domain of from 0 to 1 with points at 0.01, 0.02, 0.03, and so on. This is some density we have in 1D. If we go in 10 dimensions, basically just 10 dimensions, the number of points required to keep that density, that sampling density in terms of having points close together enough is much different. We will need then not 100 points, we will need 10 power of 20 points, which is huge, ultra huge. That means in practice that we cannot preserve the sampling density. The sampling density there will be much lower. And so with a lower sampling density, we may have more problems to model well the distribution of the data, for example. So if we are looking at the quadratic discriminant functions, we have a relatively high number of parameters. We see worse, but still compared to the other models, we have something like k times d values to estimate for the mean. So d is the dimensionality and k is the number of classes. So this is manageable, but the other one for covariance matrix is less manageable. We have a t times t plus 1 divided by 2. So it means that every time we are increasing by 1 dimensions, we are multiplying, we have a power 2 on that. So we are increasing much more the number of parameters to estimate for the covariance matrix. So when we are looking at high dimensionality with a large D, with few data, a small n, there is a high risk of singular matrices. So that means that we may get matrices cases where there are some correlation between the variables, which may be real or not, it depends. And we also have cases where we can have zero variance. This is also possible. But I would say there are many degenerate cases possible with higher dimensionality. So even with cases where the determinant of the covariance matrix is not equal to 0, we still have something that is not singular. A small change can cause a large variation. So we can induce big instabilities in the modeling of the data with a higher dimensionality. So something that we may do here is to reduce dimensionality by making use of feature selection or projection. So the point is to reduce the number of variables to use. And there are smart ways to reduce that. This will be seen by the end of the semester, among the last presentations in the last weeks. A nice example to show that is that figure. You know, it's simply going from 1D to 3D. So in 1D, we have this kind of distribution here. We have we are between 0 and 10, and we have 6 regions, 6 positions somehow. If we map this in 2D, we see that for having the same kind of thing, but in 2D, between 0 and 10 on both dimensions, to keep the density, we need to increase the number of what we call squares here, which are kind of pixels, but see this as points. We can see that we go from 6 to something much higher, which is probably 36 or around 36. And then if we go in 3 dimensions, this is even bigger. So like it is explained here, from one dimensions, we need 10 positions, 2 dimensions, we need 100 positions, and 3 dimensions, we have 1,000 positions. So given all these positions, the number of samples here to preserve density need to be increased significantly.